Today's lesson is on CAPE Physics 2, and I am Paul Bender. The topics we will be covering today is on electromotive force and potential difference. Now, at the end of this lesson, I want you should be able to differentiate between electromotive force and potential difference using energy considerations. And you should be able to differentiate between EMF and terminal potential difference of a cell, and describe an experiment to determine the EMF and internal resistance of a cell. Some of the terms I want you to internalize at the end of this lesson are electromotive force, potential difference, and internal resistance. Now, you must come into the lesson having some prerequisite knowledge, and so the expectations are that you would know an electric current is comprised of charges in motion. You should know Ohm's law. You should know the symbols for circuit components, and you should know that the potential difference across circuit components in parallel is equal to the terminal potential difference of the power source. And you should also know the equation of a straight line graph, and you should know to determine the y-intercept and calculate the gradient of a graph. Now, in this lesson, I will take you to some quick quizzes, which I want you, so if you can get your pens and your paper. And these quick quizzes are just to keep you focused on what the lesson is, and as we go along and as the lesson progresses, you'll be able to understand more clearly what it is that is happening. All right? All right, let's start with electromotive force, EMF. Now, we know that a current is a flow of charges, but in order to set those charges in motion, the energy is required. And so what happens is that the power source in the circuit converts energy from other forms to the required electrical energy. The electrical energy will move the charges, but the power sources will convert those charged other forms. So here's a quick quiz. All right. So we have here a solar cell, a dry cell, and a generator. And so I want you to match the forms of energy that these will be converted to electrical energy in each of these power sources. All right. So I'll give you a time to look, and then I'll click for the answer. All right. So this one here, you should be, let's see what the answer for this is. All right, so here we have the cell. Chemical energy is converted to electrical energy. In a solar cell, light energy is converted to the electrical energy, and in a generator, mechanical energy is converted to electrical energy. All of these are sources of EMF. So let's go back here. Now, we'll look at a definition for electromotive force. So we say that the cells convert energy from other forms to the energy. So electromotive force is the quantity of energy converted from other forms within a source to give electrical energy to 1 coulomb of charge or unit charge carriers to move in an external circuit. So in order to get these charge carriers to move around in an external circuit, the source of EMF converts energy from another form into electrical energy to move it around. So here is a quick quiz again. A cell has EMF of 12 volts. How much chemical energy is converted to electrical energy in the cell to move 1 coulomb of charge? All right, so is it 1 over 12 joules? Is it 1 joule, or is it 12 joules? So let's see, if I seem to be rushing, please forgive me. So here is the click for the answer. All right, so the answer is 12 joules. So 12 joules of energy will move 1 coulomb of charge in a 12 volt source of EMF. All right, potential difference. When charge carriers flow in a circuit, they encounter resistance. Well, when they move through a circuit, the circuit has resistance. Electrical energy is used to move the charge carriers through the resistances. This electrical energy is converted to other forms in the resistance. So as the charge moves through the circuit, it encounters resistance, but it needs energy to overcome that resistance. It's like riding a bicycle against the wind. You use a lot of energy to overcome that resistance. All right. So potential difference between 2 points in a circuit is the quantity of energy converted to other forms, and that other form is mainly heat. When you turn on your radio, you use your phone, it warms up. That's because of the current going through resistance. To move 1 coulomb of charge from one point to the other in a circuit against resistance. So potential difference is also energy converted per unit charge, and its SI unit is the joule per coulomb or the volt. Here's a quick quiz again. A potential difference across 2 points A and B in a circuit is 0 volts. All right? So which is possible? Is it that there is no charge carriers in the circuit? Is it that the resistance between the points A and B is 0? Or is it that the EMF of the circuit is very small? Well, once we have a circuit with connectors, we will have charge carriers. And so let's see what will be the answer to this one. All right. And so it's B. If there is no resistance, then there will be no potential difference. All right? There is no resistance in the circuit, there will be no potential difference. So here's a mini summary. So we said that EMF is energy converted from other forms to electrical energy in a power source. And then we said that potential difference is electrical energy converted to other forms from electrical energy in a resistance. So let's get this clear. EMF happens in a power source, and that is other forms to electrical. Potential difference happens in a resistance, and that is from electrical to other forms. All right, so that is a salient difference between EMF and potential energy. All right, so now we'll move on to electromotive force and what is called terminal potential difference. Now, when we have a battery or a cell or any source of energy, we connect the wires to 2 terminals. And if we measure, we use a voltmeter and we measure the potential difference across those 2 terminals, we say that that is the terminal potential difference. This is a battery that I have made my own cell, and we will see what this is. These are the terminals. So I can connect a voltmeter across these 2 terminals to determine what the terminal potential difference is. But what we will discover is that the EMF of a cell and its terminal potential difference would at sometimes be different. All right? Okay. So conservation of energy principles dictate that the energy acquired by charge in a source equal total energy lost by charge against external resistances. Remember, we said that the EMF will convert these other forms of energy to electrical energy, and these charges will acquire the electrical energy. And when they acquire the electrical energy, they go out into the external circuit, but then they have to overcome resistance, and they use that electrical energy. So we know the principle of conservation of energy would say that energy gained equal energy lost. All right? And so the energy acquired by the charge would be equal to the total energy lost by that charge in the external circuit. All right? In other words, we said that, in other words, it means that the EMF, electromotive force, is equal to the sum of the external potential differences. Okay? So that's also critical to understand that the EMF acquired is converted to heat and other forms of energy in the external circuit. Quick quiz again. In the circuit below, the cell has an EMF of 9 volts and the potential difference across the resistor is 3 volts. What is the potential difference VAB across the bulb? So we have a cell, a bulb, and a resistor. So the potential difference across this is 3 volts and the EMF is 9 volts. All right, so we want to find what is the PD again across the bulb. And remember that the EMF is equal to the sum of the potential differences in the external circuit. So let's see what we have for the answer. Okay, so the answer is 6 volts because the 3 volts plus the 6 volts is 9 volts and that is equal to the EMF of the cell. Okay, all right. Now, and we continue. Now, any power source is made up of materials that have electrical resistance, right? Anything you make, it has electrical resistance. And this is an inherent or thing that it comes along with it. And this resistance is called internal resistance. All right, so internal resistance occurs because these power sources are made up of materials themselves that have resistance. All right, okay. All right, and here is a symbol how we would use an electrical symbol for a cell with an internal resistance. We have the symbol for a cell, a symbol for a resistance, and it is encaged in a dashed square. And A and B represent the terminal potential, the terminals of the cell. So within this cell here, within this cell, we have an EMF, an internal resistance, and these two are the terminals of the cell. So if you measure V across AB, if you measure V across AB, that will be the terminal potential difference. But within this cell is an EMF, and this is the internal resistance that represents all the wires and whatever it is that is in the cell itself. All right? So that's how that is represented. Now, this illustration shows a cell with internal resistance R connected to an external resistance, capital R. So here we have an internal resistance cell connected to an external resistance R. So we have a complete circuit. This represents your cell, all right? But we're just showing the internal resistance and the EMF separately. All right, back another quick quiz. So it says write an expression for the EMF E of the circuit, all right? So we have our circuit. This is the internal resistance R. I just want you to keep, this is our big resistance R. And we want to determine an expression for E. And there is a current I flowing in the circuit. All right? And remember that the EMF is equal to the sum of the external resistances. All the resistance, the potential difference across the resistances that are external to the EMF, not to the cell itself, right? Okay, so let's see what the answer to that is. All right, so it says since EMF equals sum of potential difference, we can write that E is equal to IR plus I big R. All right, now, remember now, according to Ohm's law, the potential difference across here, V, and we'll call that V external, is V is equal to I big R. And so the same current is going to flow through this little one here. And so according to with Ohm's law, V in the V internal, we would call that V internal is equal to I little r. But we know that the EMF is equal to the sum of the potential differences, right? So that is why we get E is equal to I little r plus I big R. All right? Now we call I big R, we can call I big R V external. So E, that's how we end up with E is equal to I little r plus V external. All right? So that's our equation here. Good. All right. All right. Another mini summary. So two things I want you to, two key points I want you to internalize. Internal resistance of a power source causes its EMF and terminal PD to be different when connected to an external circuit. I just want to go back a little bit here. All right. All right. Okay. EMF is also referred to as the open circuit terminal potential difference of a power source. Now, what tends to happen is that because when an EMF, when a cell is connected to a power source, all right, to an external circuit, the EMF uses some of its energy to drive the current through its internal resistance. And so what happens is that the terminal potential difference drops when the EMF is connected, or the cell is connected to an external source. All right? And so this internal resistance causes its EMF and terminal PD to be different when connected. All right, let me explain this. We have this, all right? Now remember, the terminal potential difference would include both the EMF and IR. Now when you, suppose we didn't have this internal resistance, suppose the internal resistance wasn't present. Okay, I'll take this out. When you connect the EMF, then the current that would flow in this circuit would be greater than the current that would flow if you have an internal resistance, because with the internal resistance you have more resistance, this plus this, so you have less current, so that the PD across here would be smaller. All right, if you have an internal resistance, then if you have no internal resistance, then the only resistance in the circuit would be this, which means that the PD across here would be greater. So the greater the internal resistance, the less the current, and if the current is less, then the potential difference across here would also be less. Okay, so you might have cells that have the same EMF, but they don't give you the same terminal potential difference because their internal resistances are larger. So cells with small internal resistance, they will give you larger terminal potential difference. So you can have two cells, and that is what happens when your cell in your battery or in your phone or anything starts to die. It means that the internal resistance of the cell is getting larger and larger and larger, so that the terminal potential difference of the cell begins to get smaller and smaller and smaller. All right? We can discuss a little bit more about internal resistance at some time later. So EMF is also referred to as the open circuit terminal potential difference of a power source. And I think that maybe in question time I will demonstrate that to you using this equipment here. All right. All right, so we'll do some internal resistance and EMF measurements, right? Now, so far we've seen this. We've seen that EIR, the equation equal IR equal V plus AB can be written as this. E equal IR plus V external. All right? Because you remember this is A and this is B. This is V external. And what we know, and this is a prerequisite knowledge, this is your EMF here. Prerequisite knowledge tells us that the potential difference across R is equal to the potential difference across AB. All right? This is equal to this. So V external is equal to VAB. All right? So we can write IR equal to plus V external. We can write it as VAB because these two are equal. All right? Now what we can do is we can rearrange this equation, and I'll do the math very quickly for you. So we have E is equal to IR plus V external. All right? Then what we can do, we can subtract IR from both sides. So we have E minus IR is equal to V external. I little r, sorry. And then we can write this as negative IR plus E equal V external. And it looks a lot nicer when you write V external is equal negative IR plus E. Right? So we can write our equation in that way. Quick quiz again. Very quick quiz. All right, it says if a graph of V external against I is plotted, which of the following is correct? The gradient is equal to E, or the y-intercept is equal to negative R. The gradient is equal to negative R and the y-intercept equal to E. Gradient is negative R and the y-intercept is 0. Which one of these is correct? All right. And here we see that the gradient is negative R and the y-intercept. So if we plot a graph, of V external against, what are we plotting it? Against I, we will get a graph looking something like this. All right. So if we take the gradient of that graph, the gradient of the graph will be negative R. All right. I can write this. This is preferably written like this: negative R times I. So we're plotting this, that against that. So the gradient is negative R, and when we extrapolate, this is the constant. This is in the form y equal to mx plus c. The constant here would be E. All right? Okay. So I think I have this in notes. All right. All right, so we have 5 minutes. Internal resistance and EMF measurements. The circuit shown is set up. So I have this circuit here, right? This circuit. This is the EMF. This is the cell with the EMF. An ammeter, a voltmeter, and the voltmeter is across a variable resistance. All right. Now, because, and so I have the voltmeter, the ammeter, and because I don't have a variable resistance, perhaps I can explain to you. All right, I use a number of resistors in series in order to get a variable resistance. And so what we will do, we will vary the resistance, and when you vary the resistance, it means that V external will vary, because remember, V external is I times the potential difference across here. Potential difference, I times R, and if you vary R, then V will vary. And when you vary I, the ammeter will also vary, all right? So what we will do, we will take some readings of I against V. All right. All right. So we're going to move quickly, very quickly. So we're going to take some current, and the current is in amperes, but the instrument is going to read the current in milliamperes. All right, and this is potential difference in volts. All right. So I want you to focus on the voltmeter and the ammeter. Remember, the ammeter is going to read in milliamperes, and the voltmeter is going to read in volts. So you'll have to convert the milliampere reading to amperes by dividing by 1,000. All right. Okay, so I will make the connection. Connect the power source, and then we'll make some readings as we go along. All right. I can get some assistance. Someone can help me. Someone who write nice, because if you notice, my handwriting is not too good. All right. I will tell you what are the current readings and the potential difference readings as we go along. All right? All right. So here goes. All right. 69.4 and 6.83. All right. And then we go 38.6 and 7.64. And then we go 26.8 and 7.97. 20.6 and 8.14. 16.7 and 8.27. And 14.1 and 8.36. All right. So, right. So, viewers, we have some current readings, and remember now we are going to divide these here, the current, by 1,000. So this would be current in milliamperes, but we want current in amperes. So we will divide by 1,000, 0.0694. Let's leave it to 2 decimal places. 0.39, sorry. And this would be 0.027, 0.021, 0.017, and 0.014. All right, so you can plot a graph, right? This is instruction, next instruction. You will plot a graph of potential difference against current, determine the y-intercept of the graph, and calculate the gradient of the graph to determine the internal resistance. What I have done, I have done a graph. I did some work at home and I plotted a graph, but I used an Excel and it gave me the gradient and the y-intercept. You remember we did a demonstration where we got some readings, and as I said, I would like you to plot a graph of potential difference on the y-axis against current on the x-axis. And then when you get a graph, you will get a graph with a negative gradient. And this is what I had done at home, but I use a Microsoft Excel program, which gave me the gradient, which gave me the equation of the graph. So this is y, This represents the internal resistance, Y equal mx plus c. And this here represents the EMF of the cell. Actually, it's one of those square 9-volt batteries that I put inside of here. And I put in an internal resistance to make my little cell. All right. And this is pretty good. E is 8.8. And this kind of close to 20 ohms, which I use as the internal resistance of the cell. And so today we looked at EMF and potential difference. Right? Both EMF and potential difference are energy can be considered to be energy concepts. But EMF is energy that is converted from other forms to electrical energy to drive 1 coulomb of charge. All right, so it's from other forms to electrical energy. Potential difference is energy that is converted to other forms, mainly heat, from electrical energy. And that happens when this current or this charge goes through an external circuit, when 1 coulomb of charge goes through an external circuit. We also looked at potential difference, terminal potential difference, and EMF. And we said that difference comes along because in power sources there is an internal resistance, because the power source is made up of materials which with themselves have resistances, so that there is an inherent resistance called an internal resistance, and this internal resistance affects how the cell operates. So when the cell is connected to an open circuit, is not connected, if you connect a voltmeter across it, it will read what is called the EMF, or the open circuit potential difference. When you connect that cell to a circuit, because it has an internal resistance, that internal resistance adds to the existing resistance of the external circuit, and it reduces, as a result, it reduces the terminal potential difference across the cell. And then we went and we did a little demonstration experiment in which we made some measurements, set up a circuit, and we made some measurements in order to be able to determine the internal resistance as well as the EMF of a cell by plotting a graph and determining and analyzing the graph by finding its gradient and the intercept on the y-axis in order to determine the EMF of the cell and the internal resistance. All right, that's basically the lesson for today. I know that there is I don't know if there are any questions that are continue. Okay. All right. Okay, I want to talk a little bit more on the importance of internal resistance. In some, like for instance, in a motor car battery, right? When you're going to start your motor car, the battery has to drive at extremely high current. And so what you tend to find that in those batteries, you have very low internal resistance. The materials from which the battery is made of, they are very high conductive, lead and other materials which have high conductivity. And so they have low resistance. And as a result of that, because of the low resistance, when the battery is able to generate very high currents, because the internal resistance does not limit how much current can be delivered by the battery. All right. I would want to very quickly show you the so if I connect the voltmeter,
I have a little challenge here with my equipment. This is the ammeter. Just let me see if I can quickly work through how I can deal with this. All right. All right. I just have a challenge. I can't move one of the pins there, right? Because it come out. So that to rearrange it, it will be but I wanted to demonstrate to you that when you connect this EMF to an external circuit, then it drops. We don't seem to have any questions. You know, I always says when nobody has any questions is one of two things: that everybody understand everything, or everybody don't understand nothing, so they don't know what to ask. All right, so I'll keep trying to find something for me to say. I would have preferred to have some questions. All right. All right, here's a question that I will ask you. Since nobody has a question, I will ask a question. So we have a cell and an internal resistance R, and E is 10 volts, okay? And we have a current of 0.5 amperes, a current I. And that goes through an external resistance of 8 ohms. Okay. 18 ohms. All right. So the question is, what is of this cell? So we want to find out what is the internal resistance of the cell. All right. It's not a very good idea always to just take questions off of the top of your head, because sometimes it just doesn't work for you. All right. So let's see what we know. What we do know is that the EMF is equal to the current times the internal resistance plus the current times the external resistance, right? Okay. And so we can say that E minus current times external resistance is equal to current times internal resistance. And so internal resistance would be equal to this, that minus IR over I. All right. So E is 10 volts. All right. E is 10 minus I times big R. I is 0.5 amperes times big R, which is 18 ohms, over I, which is 0.5 amperes. All right. So 0.5 times 18 is 9. This would be equal to 10 minus 9 over 0.5. This is a little r. And that is 1 over 0.5, which is 2 ohms. All right. So this is a typical question that you might want to to ask. All right? Okay? All right. Okay. So here is a typical question, but for the examination, if you're going to look for examination, some of the key things that you would want to, because the CAPE syllabus requires that you know to differentiate between, and if we go right back to the objectives, all right? If we go right back to the objectives of to differentiate, this is a CAPE. These are CAPE requirements. Differentiate between electromotive force and potential difference using energy considerations. So the key thing, remember, electromotive force is from other forms to electrical within the source. PD is to other forms from electrical in a resistance. Okay, so that's all for today for CAPE Physics Unit 2.